Okay, thank you very much for the announcement song. Thanks a lot to all the organizers for bringing together this wonderful meeting, where I really enjoyed the talks already of the last week and yesterday. Yeah, so in this talk, I'm trying to report on a recent result from that paper here, together with my co-authors Jan Gerken, Axel Kleinschmidt, Carlos Mafra, and Bram Verbeek. And the goal is to introduce you some form which may generalize the beloved Parke Taylor factors to a genus 1 surface. So just to remind you once and for all, I guess I don't need to comment much on what that guy is. PT will be the notation throughout the talk. Good. Let me try to be clear about the motivation and philosophy of this talk. So admittedly, we have seen a lot of geometries and their canonical forms in this workshop, which are not related to a string worldsheet. So in that sense, this talk will be rather boring in the sense that I will closely follow the advice of string perturbation theory. But I hope the fact that this is genus 1 will reinstate at least a little bit of excitement. Okay, so I will essentially spend this talk on tree level and genus 1 and string perturbation theory, and try my best to make some analogies between genus 0 and genus 1. So the most prominent worldsheet topologies for the scattering of open and closed strings at these borders, there we have the disk at tree level for open strings and the sphere at tree level for closed strings. And by the opening line of string amplitudes that you find in the textbooks from the 80s already, whenever you put open strings on a disk, well, they are attached to the boundary, which gives rise to a color ordering. And therefore, your job is to integrate over the open string insertions with inequalities such as that. And if you perform all these moduli space integrals order by order in the inverse string tension, the kind of periods that you get here are multiple zeta values. MZV throughout the talk is multiple zeta values. The definition will come later. Now, if you do the same kind of alpha prime expansion for closed strings for the sphere integrals, then you also get multiple zeta values, but fewer of them, only the single valued subclass that will be introduced in more detail later on. And if you're interested in a specific closed string integral, well, actually you can get it for free if you exploit some connection between the integration domain on the disk with the inequalities and an extra integrand, an anti-holomorphic Parke Taylor in the closed string. So this anti-holomorphic stuff is intrinsic to the closed string. For open strings, everything is real. So you can't distinguish Z from Z bar. So the extra freedom to say Z bar in the closed string, it allows you to put some equivalent of the info from the integration ordering into a Parke Taylor factor, which is a complicated way of saying the Parke Taylor factor is the canonical form of that geometry here. Okay, and for this talk, the single valued map plays a key role as the diagnosis when you have found a pair of a cycle and a canonical form. And this is the kind of diagnosis I will be using at genus 1. So there, one loop open strings are governed by cylinders and Möbius strips. Closed strings at one loop are governed by tori. I won't touch the non-planar case, I won't touch the Möbius strip, but the cylinder will be the essential showcase to first of all tell you about the elliptic analogues of multiple zeta values that arise here. Then to secondly, tell you about analogous modular graph forms over here. And I will hopefully convince you that the single valued map going from open to closed strings, that this has a natural genus 1 uplift. So a lot of my efforts will go into defining and motivating a single valued map at genus 1. But now, to get back to the title of the talk, what the actual hero in this talk is, it will be the one loop analog of a Parke Taylor factor. It will be a certain function V of the puncture sonotorous and of its modular parameter tau, such that the single valued map effectively trades an integration cycle here for this elliptic function of the punctures in tau. So if there's anything you should take home from this talk is that you will later on meet some combinations of theta functions that play the role of Parke Taylor factors if you try to push the single valued map to genus 1. Yeah, there are several motivations for this kind of research program. One is that of a lazy string theorist who would love to do closed string calculations, but who is intimidated by the difficult integrals over the surface. An integral over the surface that you have to do on all orders of perturbation theory is more difficult by some metric than a line integral. So the open string has the comfort zone of these integration orderings, so you're naturally led to iterated integrals and can use a lot of definitions, say polylogs and the elliptic analogues. So roughly speaking, this side I consider as easy with many quotation marks. And wouldn't it be nice if the easy stuff can be massaged to give you the harder stuff as an output? So this is the bigger motivation to study single-valued maps, and I bet that there is a higher genus continuation of that story. Okay, and now for math, I hope that there will be some intrinsic mathematical wisdom for these functions V, which I claim are elliptic analogues of Parke Taylor factors. So in a certain sense, they are claimed to be dual to the integration cycles here, possibly in lines with Betty de Ramo by Verdier duality, but I don't dare to say that this kind of duality lines up with mathematically established terminology. So maybe it's me asking a question to the mathematicians in the audience. What is the clean way to characterize the duality that I'm trying to sketch? Okay, and maybe you're getting worried that we are in a chicken and egg dilemma. I'm trying to propose a single-valued map at genus 1. I'm trying to propose dual cycles for certain geometries. So what is the unknown that you should settle first? And to tell you the truth, it happened simultaneously. It was a long process over multiple years to come up with a proposal here and there that involved a lot of sleepless nights. And yeah, it was beneficial to keep both goals in mind. The more you know about this, the more you know about that, and vice versa. Yeah, is there some general question about the philosophy and setup of this talk?
So Oliver, can you say, is there any sense this factor V you talked about can be really viewed as some version of canonical form for the cylinder case? Or that's just totally out of the question?
There are a lot of properties that we know and love from canonical forms. In particular, the factorizations, I mean, the simple poles as the punctures collide, and more generally, the behavior at the boundary of moduli space. And I put more emphasis on what these guys do for tau to I infinity as you pinch the A cycle and produce a nodal sphere. Maybe I should spoiler straight away. At tau to I infinity, these V's will on the nose give you Parke Taylor factors from genus 0, or precisely a cyclic orbit thereof. So this is one of the main reasons that we are confident about our proposal, that it's consistent, among other things, with the genus 0 limit.
All right, sure, okay.
Oliver, can I ask a pre-question, even at the tree level, just to see what the analog of the answer to this question will be in what you're talking about today. So if you take the actual superstring amplitude or the correlation function of vertex operators out of the box, you don't get the Parke Taylor factor, right? You get things with double poles and so on, and you have to do some massaging to turn it into the Parke Taylor factor with integration by parts and so on. And that and it's after that massaging that you get this nice object that reflects the factorizations of the surface and is a canonical form for the region you're talking about, and so on and so forth. Are you so first of all, what's your attitude about that at tree level, the fact that you have to do this massaging to make that happen? And secondly, are you doing some analog of that massaging in the one loop examples that you'll be telling us about? In other words, you're focusing on some kind of world sheet integrand, right? Which is supposed to be the elliptic analog of the Parke Taylor factor. But what is it that you're doing to the answer sort of out of the box to bring it to that form?
Okay, to start with the second part of your question, we do massage the one loop integrands into D-log form. And the elliptic analog of D-log form involves the Kronecker-Eisenstein series that I will define later. all.
I see. So, but you have the same attitude. So you are doing some sort of massaging to bring it to as close as a D-log form as you can. But now it's not D-log. It's going to be something involving the Eisenstein theory.
Absolutely, absolutely.
Yeah.
And okay, at tree level, we have a theorem by Aomoto that we will succeed to get to a Parke Taylor basis.
Right.
And at genus 1, I'm not aware of such a theorem. So all we have is data and circumstantial evidence. More of the evidence is in progress, but I'm still burning to hear a mathematician's rigorous argument for that.
I got it. Okay.
So
thanks.
the spoiler is we believe the dimension of the twisted cohomology is n-1 factorial at genus 1. So
n-1 factorial. Okay.
n-1 factorial.
Okay.
This is something which has small differences to the V functions. These V's are not claimed to be a basis, but I can tell you about the basis after the talk.
Thank you.
You're welcome. Good. Yeah, my next step is to walk you through some tree-level basics to set up notation and give more intuition to that single-valued map. So I'll talk about how Parke Taylor factors appear at the string tree level. And many people will roll their eyes now that I throw the same kind of definitions to you that I do in most of the talks. So the toy examples for genus 0 purposes are the Parke Taylor integrals on a disk worldsheet denoted by Z, and more Parke Taylor integrals in the sphere worldsheet denoted by J. So you can dedicate one piece of notation to which Parke Taylor factor do you integrate. And another piece of notation is either talking about the integration domain. So here, this refers to which ordering of the disk boundary do you pick. And since on the sphere, we don't have a notion of ordering, you must do something else with this information here. Namely, you characterize the anti-holomorphic Parke Taylor. So here, this first slot refers to the integration cycles and its dual forms. And yeah, in this setup, let me tell you how the string theory diagnosis looks like, that this is the canonical form of that cycle here. How do we see it at the level of data? How do we see it at the level of, well, how this evaluates as a function of alpha prime? So the first indication that cycles and forms have something to do with each other is looking at the alpha prime to 0 limit. So in both cases, both for the disk integral and for the sphere integral, you can pull the biojoint scalar out of these Parke Taylor type integrals on the board. So they have a shared alpha prime to 0 limit. The disk integral over a cycle and the sphere integral where an anti-holomorphic Parke Taylor takes the role of the cycle. So this is the first data set underpinning that duality. And even beyond the field theory limit, the entire power series expansion alpha prime confirms to you that you should compare disk cycles with Parke Taylor factors. Namely, for the alpha prime corrections beyond the biojoint scalar, these two types of integrals are related by the so-called single value map of multiple zeta values. The definition will come in a second. So this notion of single valued multiple zeta value, it was introduced by Schnetz and Brown, and there's a variety of authors from math and physics who worked on understanding why the disk and sphere integrals are related like that. Alpha prime expand the disk integral, work out your coefficients in terms of multi-zetas, and hit them order by order in alpha prime with a single valued map given by these fellows. So this is one recipe to get the sphere integral for free. Remember, I consider the sphere integral as hard because it's a two-dimensional integral per puncture, and it's enchanting to get it for free once you know the disk integral in its alpha prime expansion. Okay, I should give you more and more information about that single valued map. First of all, I should introduce the multiple zeta values. They are East Coast and West Coast convention to how you order the labels to it. So here I'm indexing the multiple zeta values by a bunch of integers n, and these integers n, they refer to the exponents of certain summation variables k. So here are more integers k that we sum over in this nested manner, such that you cannot freely swap the different n's. So this is a multiple zeta value with integer n's, and let's make the sum converge by dialing the last entry. And we know from the math literature what the single valued map is for each of them. And it's simplest to state the rule at depth 1 when you have the Riemann zeta. So there, the single valued map is as simple as killing the evens and doubling the odds. So there is no room for zeta even in single valued, and there are some factors of 2 for single valued odd zetas. Okay, so let me unpack the relations that I wrote down in huge generality before. Let us look at this in the simplest 4-pointer setup, where we can evaluate both integrals in terms of gamma functions. And we can use standard results about the expansion of these gamma functions. And this gives rise to exponentials of that type. I hope this is not getting too small. So roughly speaking, you have a simple pattern of zeta values in the exponent with some dimensionless Mandelstam invariance. And just by inspection of the exponents, you can convince yourself that this rule here, this single valued map at depth 1, is precisely the gadget you need that takes you from the disk to the sphere. Just you filter away the even zetas and you double the odd zetas. This is precisely the observational tweak to get from here to there. Yeah, so this is some first empirical remark on the single valued map. And in the next step, I will tell you more about its origin and what the funny terminology single valued multiple zeta value means if it refers to just the number. Is there any question on that before I go a bit deeper into the single valued map? Oh, whiteboard. I thought it's a blackboard talk. Sorry. Okay, I will now try to motivate where the single valued multiple zeta values come from. Oh. Okay, let's really stay faithful to the blackboard. So the notion of single valued NZVs comes from polylogarithms. Let's use the following notation for the meromorphic polylogs. So this is almost the Goncharov G notation, maybe up to a reversal. So polylogs at genus 0 are iterated integrals over a path from 0 to z. So the argument is here, the upper end of the integration path. And then the entries A refer to the log forms. And I'm sure all of us have their personal history to play with these things. I'm setting the labels to be 0 and 1 for simplicity, but there's no trouble to introduce some further punctures different from 0 and 1. Okay, and the key observation on these meromorphic functions is that they have monodromies as you deform the integration contour. Namely, you get monodromies as you wrap the contour around 0 or likewise 1. Obviously from the singularities of the integration kernel. And maybe you don't like these monodromies and prefer a single valued function. And good news, you can cancel these monodromies by adding the complex conjugates of the polynomials. So this can be illustrated with a dump weight 1 example. If you just put a single label into the polylog, then it's actually a logarithm in the conventional sense. And we clearly know it's monodromy, and we clearly know how it can be promoted to be single valued. you just need an absolute value square. So this tweak of putting an absolute value square, this is the simplest example of a single valued polynomial. But this trick not only works at weight 1, it can actually be done at all weights by being sufficiently creative to sprinkle in the complex conjugates. So the next piece of information is, how do you define the higher weight analog of a single valued polynomial? And you need a little bit of a guiding principle. There is one by hand choice that you need to make. Do you like the holomorphic derivative or do you like the anti-holomorphic derivative? So usually one chooses one of del z or del z bar to be nice, and then it uniquely pinpoints which anti-holomorphic things do you need to add. So if you do the same at higher weight, the defining property of the single valued polynomial is that this map should preserve d by dz. Okay, so to say it slowly, the differential equation is obviously of this type that you clip off the last entry and replace it by a simple pole. And now, whatever the single valued version is, it should by all means satisfy the same differential equation where I put an SV on both sides. Okay. Furthermore, I want to see no monodromies, and I want to see the same evaluation at z equals 0 and z equal 1. So with this kind of extra input, you really pinpoint these functions themselves. So you get combinations of polylogs and their complex conjugates. You just saw a simple weight 1 example. Yeah, so this construction was firstly done by Francis Brown in 2004, where he gave a beautiful generating series for these ISVs. Now, as I said, you can write these ISV as combinations of meromorphic polylogs and their complex conjugates, but there's an alternative viewpoint, an alternative representation. I'll now give an integral formula how you can realize these requirements by making use of Parke Taylor factors. So once you have the duality between disk orderings and Parke Taylor factors on your side, you can convince yourself that there is a nice integral formula for that single value polynomial. And yeah, before I state it, let me give credit to Brown and Dupont, who nailed it as a theorem that this integral formula works. Okay, so on the meromorphic side, this ISV should closely follow its meromorphic friend. And therefore, we copy-paste all the meromorphic parts of the integration kernels. So this is exactly the same as before single valued, but now I need to do something about the integration ordering. So that integration ordering will now come in through a Parke Taylor factor, or more precisely, an SL2 fixed version of it. I hope you can still read that. Okay, And the integration domain, this is just over many copies of the Riemann sphere modulo the diagonals. Okay, and normalization works if I put a factor of minus pi to the double. Okay, so this is giving on the point the single valued polylog. It's a different question how easy it is to evaluate that integral, but it is an object with all the defining properties. It's a single valued in Z bar, or well, in Z by inspection, so to say. And you can also check that the holomorphic differential is doing what it should in a very, very loose sense. You do the holomorphic derivative right here and get a delta function. Okay, but let's say for a mathematically rigorous discussion, I will refer to these guys. Okay, now let's get back to multiple zeta values. So what does this setup of single valued polylogs have to say on which zeta values occur in the closed string? The single valued map, it commutes with the holomorphic differential, but it furthermore commutes with evaluation. So you inherit a single valued map of multi-zetas, more precisely their motivic versions. So you just commute the single valued map with evaluation. This is a fancy way of saying, let's remember the polylogarithmic origin of multiple zeta values. Namely, this is up to a minus sign, a special choice of polylog evaluated at 1. And the code of zeros and ones here is related to the arguments of the zeta. Oops, this is the last n. Okay, so we know precisely which kind of single valued friend belongs to this guy. So let's evaluate the single valued polylog at the same sequence of zeros and ones, also at z equal 1. And that defines for you what a single valued multiple zeta value is. Good. So you can view this as being an induced map. We have good control on the polylogs, and then the multi-zetas do what they have to do by evaluation. Okay. Yeah, so this is a key feature of how the single valued map works at tree level. And I will now mimic this at genus 1 in the rest of the talk. And let me just recapitulate the key point. What is the key reason that the single valued map takes disk integrals into sphere integrals? It works because the boundary of the disk integration cycle becomes the simple pole of the Parke Taylor factor. Yeah, what you understand under a canonical form. And in particular, you stick in anti-holomorphic Parke Taylor factors, which commute with the z derivative up to delta functions. So this is the gist why that genus 0 setup works so well. And I hope I can convince you that we can reproduce that in a genus 1 setting. Any further genus 0 question? Okay, let me start with some basic facts about one loop string amplitudes. I'll try to be really basic and mostly draw pictures. For instance, tell you about my favorite parametrization of the torus. So here that closed string worldsheet at genus 1. It has obviously 2 homology cycles and a nice parametrization of that guy through a complex coordinate goes as follows, that the 2 cycles become two periodic directions. So for one of the cycles, let's call it the A cycle, you identify those two. And for the other periodic direction, you identify this and that. And of course, you can use conformal invariance to decide one of the periods is 1, and the other period is what it is. This is the modular parameter tau in the upper half plane. Okay, so this is the closed string geometry where I would like to map you with some single valued map later on. And here is the analogous open string worldsheet. There are actually two options how you line up the periodic direction. I will design the cylinder such that the boundary is sitting on the imaginary axis. So I take the cylinder boundary to go between 0 and im tau. So let's put all the punctures here. So then we have here Z1, Z2, dot, 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 Zn. Needless to say that you could go non-planar, but I will skip this for simplicity. Okay, and yeah, strictly speaking, the moduli in the cylinder, they only have one real degree of freedom, or putting it differently, you can choose both tau and the punctures to be purely imaginary. And now there is again a notion of ordering, since you put open strings on the boundary. There's again an integration cycle defined by such inequalities. And in the given parameterization here, the integration cycle ends with tau. Good. These are the pictures. This is the rough geometry. Now it's time to say something about the integrands. So clearly, your job in computing a one-loop string amplitude is to integrate over all moduli, both the punctures and the modular parameters. And let me describe that in 2 steps. Say you want to do the tau integral last. So roughly speaking, the closed string amplitude is a tau integral of something which comes from doing the z integrals. So I need some function where all the z's are integrated out, and it will depend on tau. And it must depend on tau on a modular invariant manner. You only integrate over the keyhole region, which is a fundamental domain of the modular group SR2Z. And consistency requires that the tau integrand is a modular invariant, that it has these invariances under the generators of the modular group. Okay, so to already give a preview, at genus 0, I wanted the polylogs to have no monodromies in Z. And now, here there is a single valued flavored criterion on tau that we want to have a modular form. This will be a key ingredient of single valued integration at genus 1. Okay. And to give even more details about this tau integrand, this is, as I said, the result of integrating out the torus punctures. So the obvious part is that you integrate many, many times over the torus T. And here is more notion of single valuedness. Whatever your integrand for the Z is, it should be a well-defined function on the torus. So it should be the same under translation on the A cycle, and likewise translation on the B cycle. So
Oliver?
Oh, yes, please.
Maybe you can move your camera to the other side. Yeah, great. Thank you.
Good. So this is some added part of the criteria for what it means to be single valued at genus 1. Okay, and the analogous statements for the open string. The analogous open string cartoon goes as follows. Say we integrate over the modular parameter last. So here there is no keyhole region, but instead you have to integrate over the entire imaginary half axis. If you're worried about UV divergences, there's the Möbius strip that rescues you. But for what I'm doing today, there is no need to talk about that. Okay, so now you will have some function of tau, which results from doing the z integrals. And now there is more information about the z integrals. You do them in a way that singles out an integration cycle. And this is for what I want to propose, a dual form. Okay, so there is a function h similar to the one here that lives on the cylinder. Yeah, and to already do the name dropping, what are the kinds of periods of the configuration space that we have in this F and in this H? So here the cylinder integrals, the result of integrating out the punctures, are so-called elliptic MZVs, defined by Enriquez. And in case of the closed string, these are certain non-holomorphic modular forms, the so-called modular graph functions. Introduced by Dokor, Green, Gürdogan, and Van Hoof, and who really enjoyed a lot of attention and have quite beautiful structures. And yeah, one of the results for today is to give you an explicit map, taking you from an elliptic MZV to a modular graph form, such that you preserve the holomorphic differentials. But okay, let's stick to the step-by-step procedure. The next information I want to give you what's inside these H. What are the integrands for the punctures and the moduli? So this touches upon Nima's question from before. What is the most general atom of these integrands? Or what is a universal currency to express the correlation functions that come from the string amplitude prescription? So the atoms here, these are, if you wish, the genus 1 versions of the D log Z forms. The atoms come from conformal field theory on a torus. And the guiding principle is you have to know your integration kernels. At genus 0, we were fine with 1 over z minus w after integration by parts. And here, you need an infinite number of integration kernels that take the role of the 1 over z minus w. This may at first sound a bit disturbing to have infinitely many, but you can nicely generate them from a so-called Kronecker-Eisenstein series. So I give you a generating function for all these F kernels. And this is the moment where I have to write down a theta function. don't worry too much if the theta functions are not your daily bread and butter. I will highlight which properties you need to know. Okay, there is the Jacobi theta 1 function, which is odd and which produces a simple pole at the origin. This is an odd function, and if you're close to the origin, then theta of z goes like z itself. So therefore, this has a simple pole at the origin, and the residue is quite boring. The residue is independent on eta. Yeah, talking about eta, what the hell is this additional variable eta doing here? Well, I'm promising you a generating function, so you should expand in that eta variable. So you can do a Laurent series in eta, and then each coefficient in that eta expansion, well, it's some function of z and tau. Okay, and simplest examples are so F0, this is the residue of the simple pole in eta, and it's not hard to see that F0 is 1. So there's a very boring member in our club of differential forms. And to show you the first non-trivial integration kernel, we have the F1 function that comes from a d log theta 1. And there's also some contribution coming from that exponential. So there's also a plus 2 pi I in z over in tau. And here, this is the only singular kernel in the family of FKs. This has a simple pole at the origin and is otherwise gradient. So if you wish, F1 is the direct analog of d log z. But there's additionally an infinite tower of further forms, which are regular and which you need in order to get an analog of a partial fraction identity. That's the so-called Fay identity. But I don't want to dwell much on the higher order ones. Instead, let me comment on this exponential. Since you heard the buzzword meromorphic several times in this talk, maybe you find it disturbing to see something non-meromorphic. So the reason for that is we want to have a doubly periodic function, the torus. It should be invariant, understanding z goes to z plus tau. And also, we want to have modularity, as tau goes to -1 over tau. So just to give you one of the key relations, the modularity is such that this is identical to this move here. Yeah, and the criteria of single-valuedness and modularity, they are unfortunately not working in a purely meromorphic setup. So this is, if you wish, the minimal tweak to hardwire double periodicity and modularity into these mostly meromorphic Kronecker-Eisenstein kernels. And here's a concrete example. Maybe this is something you have seen in Kolchinsky or Green-Schwarz-Witten, that this is the doubly periodic completion of that. Yeah, so this is the alphabet of forms with which you need to play a genus or a genus 1 surface. Are there any questions on this? Okay, now let's see what we need to do to get a single-valued map. And more importantly, what are the kinds of zeta value analogues that are acted on? So now I come to the wish list for genus 1 single-valued map. Good.
Sorry, Oliver. sorry to interrupt. Maybe I should have asked this 20 seconds ago. Can you say again, what's the invariant significance of that generating function? These are all of the objects we could ever care about that are doubly periodic and transform nicely under modular transformations. Like what's special about that list of objects? Sorry, you said it. Can you just say it again?
I didn't say it properly. Okay, statement 1, Brown and Levin like them. If you want to generate all homotopy invariant iterated integrals on the torus, then these FKs are sufficient. These guys generate the full system of elliptic polynomials. And secondly, as a string theorist, I want to have a good language for CFT correlators. And for all massless vertex operators in 10D string amplitudes, I can represent their correlators in terms of these FKs.
I see. So the analog of this at tree level would be like all objects with any poles in Zi minus Zj rather than just Parke Taylor, or I mean, in other words, is this before or after integration by parts identities? That's what I'm asking.
Good question. Yeah. Before IBP, you can get a Z derivative of FK, and you furthermore can get a product of FK1, FK2 at coincident points.
I see.
And you can use successive IBP to avoid both. There's no derivative of FK anymore, and there is no product of coincident FKs.
Okay, so these guys really are the kind of analog of just Parke Taylor. What you get after IBPs puts it in this nice form.
Exactly.
All right, thank you.
I should give key credit to Dolan and Goddard, who did it for their heterotic string, and also to Tsuchiya, who evaluated the RNS spin sums, and that we revisited in our EMZV paper with Brödel, Mafra, and Mattes. Good. Yeah, so what we just talked about was the most general integrand with respect to the Z's. And let's now discuss a system of iterated integrals that captures all of that. And remember, I'm studying the tau integrand after integrating the Z's, so tau is not yet integrated over. So let's study the following iterated Z integral. It's pretty similar to what you did for NZBs. You take a couple of basis forms. This is no more a D-log, but instead it's different F's with different integer superscripts. And a good normalization choice is if you rescale them by some power of tau. So for the experts, this is the B cycle, EMZB, in contradistinction to the A cycle, EMZBs. Okay, and the number of entries is referred to as the length, and the transcendental weight is the sum of all of these ends. Yeah, and now I want to ask, what is a sensible notion of a single valued map of an EMZV? So what are the properties that I may wish for? And here I need to intensely wave my hands and make analogies to the genus 0 case. So we want to now connect with a typical closed string quantity. For closed strings, you don't integrate over a cycle, but you integrate over the entire surface, the torus. And in particular, you eventually want to get a modular invariant integrand. So one of the requirements on a single valued EMZV is that you want to have a combination of modular forms. Good. Then we saw at genus 0, it was important to evaluate namely at z equal 1 to get single valued MZVs. And also here, I want the single valued map to commute with evaluation. And here, the most important evaluation is at the cusp. So I'm looking for a modular form whose expansion around the cusp looks pretty similar to expanding that guy around the cusp.
Or Oliver?
Yes, please.
Is there an upper limit of your integration domain in the
Oh, yes, there is. Thank you. So sorry for forgetting that. You integrate over the B cycle. And actually, there is a second family of EMZVs where you put 1 here, where you integrate over the A cycle. And they are, if you wish, a doublet under modular transformations, that A cycle EMZVs get mapped to B cycle EMZVs under the modular S transformation. But for closed strings, I don't want to have a modular doublet. For closed strings, I want to have a singlet. So the goal is to get something which really transforms as a modular form. Good. Yeah, so on this second point concerning the evaluation, it's quite similar to polylogs. You do get MZVs and these limits. Roughly speaking, the torus degenerates to a nodal sphere, and both of the EMZVs and the associated modular graph forms have an expansion around the cusp with MZVs. So you can use the SV map on the multizetas at the cusp in order to check if it commutes or not. Okay, so what else should genus 1 single valued map do for you? It should furthermore commute with the holomorphic differentials. And again, for the experts, you can only work on the holomorphic side, but you can't simultaneously bring the anti-holomorphic side into good shape. So I don't want to make any postulate on d tau bar. Okay, now comes the most important point. I want to have an analog of this integral formula for single valued polylogs. Remember, there was this integral formula for ISV, where you copy pasted the meromorphic D-log forms and where you inserted a Parke Taylor. And I want the same to be possible at genus 1. I want an integral formula that sprinkles some tau bars. But the important point comes right now. I want to have the same meromorphic integrands. Well, I shouldn't say meromorphic, but maybe almost meromorphic. I told you about these little MZ pollutions inside the Fs, but never mind. I want to have an integral formula where now I integrate each puncture over the torus, and the information about the ordering is going into some magic function. Which only depends on the z bars. Now at genus 0, this is where you would have a Parke Taylor factor. And now I'm giving you an object V that you should put here instead. And admittedly, this is close to a chicken and egg dilemma. I'm telling you that we want a single valued map. I'm telling you that I want a function V that I can put here. So the problem is somewhat to solve for both the SV map and for this function V. Okay, so the main result of the talk is this one, and I should speed up to spell it out before my time ends. I admit I'm already cutting a few corners out of timing reasons. I will later on send you a slightly extended version of this talk in form of handwritten notes that maybe we can put it on the workshop website or some other place.
Sure. Thank you.
Okay, so let's now get to the key ingredient. The genus 1 analog of Parke Taylor. Okay, so step 1 is to recycle structures that you already know and love from genus 0. So we do a Parke Taylor type cycle of the Kronecker-Eisenstein series. So remember, omega is this generating series of the F kernels. And now you can put all kinds of differences of functions in there. You can form a ring out of these Kronecker-Eisenstein series. And I'm using the same expansion variable Ada for all of them. And what is cool about this ring here, the imaginary parts in the exponent cancel. So because of the ring structure, this is indeed meromorphic. But at the same time, it's doubly periodic in all the punctures. So this is one of the rare elliptic functions. Maybe the simplest one you know is the Weierstrass-P function. But these are elliptic functions in n punctures. And actually, it's a generating function full of them. Let's now expand in the Ada variables. And we are elliptic at each order in Ada separately. So this is a generating function of naively infinitely many elliptic functions in n punctures. Okay, and also if you look at the singularities, omega has a simple pole. So the singularity structure is just like the tree-level Parke Taylor. But now there is a doubly periodic completion coming from all the theta functions in there. Okay, since I'm promising you modular forms, it's worth noting that this subscript is on the nose, the modular weight. Or more precisely, it's a holomorph modular weight. Good. We are almost there. Now there are several choices of W. Which one should I take in order to form the genus 1 Parke Taylor? So here, the idea is to combine different V's. And I'll tell you in a minute why. So let's first state the claim. Let's be democratic among all the VWs, at least up to and including modular weight n-2. Now let's put certain relative factors, including 2 pi I and including some inverse factorials. Okay, it's a finite combination of these V functions, and it's really an easy task to expand it back into the FK kernels. It's just finitely many terms, and each one can be assembled from the FK kernels using this generating function. So you always deal with finite combinations here. Nothing too scary. But who tells you which of the exotic relative factors to pick? And this is, in fact, information from genus 0. So here, it's the consistency with the genus 0 single-valued map that strikes. So the coefficients can be uniquely solved for if you demand a consistent genus 0 limit. they are engineered for the following purpose. Let's look at how to infinity. At this boundary in moduli space, I want to recover something that I know. And what I like the most, maybe I first draw the picture. What I want to recover is a nodal sphere together with a Parke Taylor factor on that nodal sphere. So this is the nodal sphere that emerges from this Pac-Man figure due to a degenerate torus, where you identify two genus zero punctures at 0 and infinity. So you should expect Parke Taylor factors in n+2 punctures. And it's the punctures on the Riemann sphere. These are the so-called sigma values, the exponentials of z. Okay, so what you want is an SL2 fixed Parke Taylor factor. And you also need to transform the dz's into d sigma over sigma. Okay, so here it's the promised combination of Parke Taylor factors on the nodal sphere. Yeah, you get this nice cyclic combination, and this is the reward for tuning the relative coefficients in the way I did. Or to be honest with you, this is what we postulated and then engineered the coefficients to attain that. Good. Yeah, I hope you give me another 5 minutes to walk you through examples. I apologize for the suboptimal time management. Yeah, so we looked at ENs and Vs, which are iterated integrals over as many torus punctures as you like. And let me give you the respective dual. Okay, this is probably fairly easy. This maps you to the function V01. There's an extra puncture at the origin. And if you unpack the formula for Vn from the previous blackboard, then this gives you 1. Quite a boring case. So I should urgently give you a non-constant example of these V functions. Say, if you are at one multiplicity higher, then you get this. And this V1 function in turn, this is a combination of simple poles. So here is these F1s. Okay. And maybe the last example for today, as you go to multi-integrals, then you simply pick up more terms. Okay, and you get more and more possibilities to get singularities as the punctures collide. Yeah, it's quite similar to anti-holomorphic Parke Taylors. The longer your chain goes of Parke Taylor factors, the more mutual singularities you can have among them.
Sorry. May I ask a question?
Please do.
The modular weight of V1 and V2 are different. So how can we add them up?
Oh yeah, this is true. Yeah, I was quite modest 20 minutes ago when I just postulated a combination modular weights. So here you need a lawyer to decipher my talk. I didn't claim that they are uniform in modular weight, but it should be a linear combination of modular forms. I admit this is strange. And the way I recommend you to think about it, you can take linear combinations of different symmetry properties. You can do symmetrized cycles, you can do anti-symmetrized cycles, and each symmetry component has its own modular weight.
Okay.
As perverse as this may sound, the temptation is to assign a modular weight to an integration cycle. So symmetrizing the open string punctures, as for instance in photon amplitudes, is associated with a cycle of quote-unquote modular weight 0.
Okay, thank you.
Yeah. Good, I should really wrap up. So the central result of this talk is the proposal here for an elliptic analog of Parke Taylor's. Oh, sorry, the proposal is on the neighboring blackboard. Yeah, the proposal is this guy here. The reason why we believe this is a good choice is it's consistent with anti-holomorphic derivatives, with the degeneration at the boundary of moduli space, with modular properties. You can also check that the singularities, namely the simple poles, are in perfect correspondence to the boundary of the dual integration cycle. And again, the word dual deserves a lot of quotation marks, since we haven't lined it up with, say, mathematical notions of Betty-de-Rham or Verdier duality. Yeah, some hopefully related work I should mention. Also in Francis Brown's papers, we find single-valued iterated Eisenstein integrals. We are confident that this will eventually reproduce Brown's single-valued iterated Eisenstein integrals. We haven't managed to check it either at the abstract level, and we also haven't studied examples of high enough weight, but it's quite likely that this is just coinciding with Brown's notion of single-valued iterated Eisenstein integrals. Then a second comment, there's a talk by Erik Panzer at String Math. I think it's at 6 p.m. Uppsala time, in maybe 3 or 4 hours from now. Yeah, I believe that this will be closely related to here, maybe with an even broader perspective to other areas of physics where single-valued integration occurs. And final comment, back to the string theorist's motivation. As I said, I want to get closed string quantities for free by doing simpler open string calculations. So far, we don't have a proof that the endpoint function of closed strings can be written in terms of integrals over these. It's the case for the 4-point and 5-point function in 10D type 2 theory, but it's under investigation what happens at higher multiplicity. There is a subtlety concerning if these guys span the twisted cohomology or not. But if you want to see a basis or a conjectural basis for the twisted cohomology, ask me after the talk and I can give you some more general arrangements of Kronecker-Eisenstein series. Yeah, I think that brings me to the end. Thanks a lot for your attention.
All right, thank you, Oliver, for this very impressive Blackboard talk. Questions?
Oliver,
So,
is this
Oliver,
go ahead, Sung. Sorry.
Go ahead. No, you go ahead.
Is this principally useful in the alpha prime expansion?
Oh, yes, indeed. In the closed string alpha prime expansion, you want to learn about the effective action, the one-loop effective action. And you need to evaluate the modular graph forms, including their behavior at the cusp. Maybe the most difficult part is to nail them at the cusp. And you can use this to get conjectural expressions for modular graph functions at the cusp. It's about the innocent sounding task to detect a plus zeta value when you expand a modular graph form around the cusp.
But the sort of statement about these guys giving you everything you want, even for open or closed strings, is in the alpha prime expansion. I mean, you're saying that everything that you see in the alpha prime expansion is one of these guys. Is that right?
In the present formulation, yes. And
yeah,
it's a daunting task to extend it to beyond alpha prime. Yeah, best illustration about the beyond is look at the gamma functions at tree level 4-point. You change the structure of poles and zeros under the single valued map. And I don't understand how this works at tree level beyond 4 points. So yeah, a lot to do. I think these infinite product representations are essential that we discussed 2 years back in time.
Right.
Yeah.
Thanks.
Hi, can I ask also a question, or are we too short in time?
Please go ahead, Piotr.
Yeah, it was, hi Oli, kind of following up on Nima's question. I was wondering, because so it's going to be sort of a naive question. This definition of Parke Taylor factors, they seem to. Is there an alpha prime in the formula you wrote on the blackboard in the box just there? Alpha prime to some power?
There isn't. Yeah.
There isn't.
Yeah.
And so because these omegas, you kind of always need to expand them, and somehow secretly they must contain an alpha prime somewhere, right?
Okay. Yeah, this is a bit subtle. Yeah. We do study certain generating series where these variables are on similar footing as the Mandelstams. There are certain generating functions of torus integrals where you find combinations like this inside a gamma function.
Okay, so eta has an alpha prime.
Yeah. And these etas, they're super weird. They are somewhere in between a Mandelstam invariant and a puncture. I mean, the reason to diagnose a puncture-like property is by just looking at the theta functions. You have theta functions at argument z plus eta. So I think there's a lot more to learn about this theta.
Yeah, right.
It's a hybrid between a Mandelstam and a puncture, to say it in very loose terms.
Because the tree level of Parke Taylor is really a term that doesn't talk so much to the exponential, while this language or this formalism is kind of geared towards expanding the exponential of the Kobe-Nielsen factor. Am I wrong?
It's partly true. If you want to have some auxiliary integrals to do the amplitude on your table, then indeed, then it works like you're saying. But there's a case in heterotic strings where you get these guys next to next without any alpha prime. So specifically, take 4 gluons in heterotic string, and the correlator is something like G4 times a B4 function times G6 times a B2 plus G8 times B0. So G are the holomorphic Eisenstein series. And yeah, every term has the same modular weight. And this is the schematic form of the 4 gluon correlator in the heterotic string at 1 loop.
Okay. Okay, thank you. I have more questions on this, but I'll ask you later. Thanks.
Thanks for your question.